Assalamualaikum and salam sejahtera. Today I will give lecture on BMCG 3113 Solid Mechanics 2. At the end of this course, the student should be able to evaluate and solve buckling problem of structure members under compressive axial loading. The topic that we will discuss about column on direct load part 1. The content for this slide is introduction, stability of structure, Euler formula for pin-ended column. The design of column cross-section area is selected such that stress equal to P over A, below than stress available. The deformation equal to PL over AE, not exit then deformation specification. After this design calculation, may discover the column unstable under loading and suddenly become sharply curved or buckled. The load applied at AB column, if the P increase, the AB column will buckle. The long slender members subjected to axial compressive force are called column. The lateral deflection that occurs is called buckling. The maximum load a column can be supported when it is on the verge of buckling, called the critical load or P critical load. P critical applied at column. If the P load increase over than P critical, the column will buckle at the midpoint. Consider model with two rods and torsion spring. A small perturbation become P times L over 2 sin delta theta equal to P times L over 2 delta theta equal to this stabilizing moment. The column is stable if P times L over 2 delta theta below than K times 2 delta theta, so the P critical become 4K over L. Assume that load P is applied after a perturbation. The system settle a new equivalent configuration as deflection angle. So the P times L over Pk equal to P over P critical equal to theta divided by sin theta. Nothing that sin theta below than theta. The configuration is only possible if P above than P critical. The moment equal to minus P times Y. This is a P, this is Y. The equation bending become d2y over dx2 times P divided by EI times Y equal to 0. This is the general solution using boundary condition at A. The constant B become 0. At bending moment at point B, then A sin square root PL over EI become 0. Disregarding trivial solution for constant A equal to 0, we get sin square root PL over EI equal to 0, which is specified by square root PL over EI. So this is the Euler formula. The n value depend on the type of the load applied at the column. N equal to 1, 2, 3 and so on. The smallest value of P obtained for n equal to 1, so the critical load for column is P critical equal to pi power of 2 times E times I over L power of 2. This load referred as the Euler load. Then the buckle shape defined by this formula. The maximum deflection Y max occur at the midpoint of the column. This is the neutral equivalent for the the column. If above, the column unstable, below the neutral, the column unstable. A column will buckle the principal of axis as least moment of inertia, the weakest axis. For example, shown buckle about the A axis, not at B axis. So the circular tube have excellent column, and square tube also for I inertia at X axis and I inertia at Y are same, so the column was excellent. So this is the Euler formula for pin-ended. P critical is the maximum axial load, E for modulus of elasticity, I is the modulus of inertia, L is the length of the column. So column has various types of support. First, fixed at B and free at A, so L effective equal to 2L. Boost and pin, A pin, B pin, L effective equal to L. One fixed at B and one pin at A, so the L effective 0.7L. Boost and fixed at A fixed, B fixed, the L effective is 0.5L. Thank you.